Hello, welcome back to today's challenge. So today's challenge is a very interesting problem, which is still tree problem, but that can also be a graph problem when it comes to the approach that we solve. So the problem statement is this: so we have to find the minimum diameter after merging two trees. So there are two undirected trees, which is undirected graph with n and m nodes, numbered from 0 to n minus 1 and from 0 to m minus 1 respectively. You are given two 2D integer arrays, edges of the first tree and edges of the second tree. And edges, I is AI and BI indicates that there is an edge between A and B. Or for the second graph between U and V indicates that there is an edge. And we must connect one node from the first tree with another node from the second tree. And we need to return the minimum possible diameter of the resulting tree. The diameter of a tree is the length of the longest path between any two nodes in the tree. Look at the example. So let's say for the tree 1 and the tree 2, so the longest distance between any node in the first tree and then the second tree after the diameter of the first tree is what? 2, right? And diameter of the second tree is 1. After we merge, then we can merge 0 to 0. Then we can see that after the merged graph diameter will be 3. This is very simple, simple two trees. And look at the second example. For this case, so we are still given two graphs. So the intuition is we can connect to any nodes. Let's say the 6 can be connected to 7, but we need to, our problem statement is that we need to return the shortest distance or the diameter, minimum diameter of after we merge these two trees. So again, the two graphs were given. We can see that the simple intuition is we need to find the center of the first graph and the center of the second graph and connect that centroid, right? For example, for the first graph, the center seems like to be 0, right? Let's say from 0 to 2 and 4 is 2, from 0 to 3 and 6, 2. So basically 0 to be the center of the first tree. And the second one, again, right, the 0 seems to be the center. From 0 to any node at maximum, it's a distance 2, right? So we can basically connect these two. So the diameter of this after we merge, it will be like diameter. We need to take the half, right? Because 2 from 4 to 2, 1 and 2, and from 0 to 0 another 1, then from 0 to 3 and 6, basically that will be a total of 4, half of 4 and half of another 4, which is 2, 2, and plus we need to connect with another edge between 0 and 0. So total will be 5. And these are the constraints. So let's look at this nodes. So for the first graph, we are given this two edges of the first tree and the second tree. So the first thing is from 0 to 1. So basically from 0 we have a connection to 1. From 0 we have connection to 2. From 0 we have the connection to 3. So this is how we built the graph. and from edges 2, 0 to 1, there is a 1 connection, right? So we can connect 0 and 0, 0 of the first tree to 0 of the second tree. So from here to the edge, that will be 1, and from here to the another edge 1, and we need another edge to connect these two trees. It will be 1 plus 1 and plus 1, that will return 3. And the second graph is a little more complex. So tree 1 is that's from the given edges we can reconstruct, or we can construct this tree, and we can see that the maximum distance between any two nodes of the first tree, you can see that's between 7 and 6, or 4 and 6, or 5 and 6. All distance is 4. That's basically, that's called the diameter of a tree. Diameter in the first case is 4. And for the second case, we can start from 4 to up to 6. We can see 1, 2, 3, and 4. Total is 4. From 5, if we come from 5, it will be the same saying. 1, 2, and 3, and 4. So basically, the diameter is the longest distance between any two nodes of a tree. That is 4. Basically, the radius of this tree will be 4 divided by 2, which is 2. The same thing here, diameter is 4, and the radius, which is basically the center of the graph, is located at 0, and distance from to any farthest edge node is basically 2, and we can add this 4 divided by 2 is 2. So then once we merge these two trees, and you can see from here 1, 2, and 3, 4, and 5. Basically, radius of this is 2, and radius of this is 2, and once we add 2 plus 2, and there is extra edge is needed, one edge, and 2 plus 2 and plus 1, 2 plus 2 plus 1 is basically 5. After we merge this two tree, our diameter of this merged tree will be 5. So the intuition is that we have to find the center node of each tree, or we need to, like, we don't have to determine this center node, but we need to get the diameter of the tree. So how we gonna find the diameter of the tree? Basically, diameter is the longest distance between any two edges of the tree. So in our case, the tree is the graph. A tree is basically a simpler form of a graph, but this case is basically, it's not the binary tree, it's a different kind of tree, right? That's basically a graph. So we're gonna use the BFS with Q. So we start, we run in this graph, or in this tree. We need to find the diameter of this tree. How are we gonna find it? So intuition is we can have two BFS. We're gonna run. We need to run BFS twice. So in the from the first in the first iteration of the BFS, what we need to do, we can start from any node. Let's say from a node 0. From a node 0, what we need to do, we need to find the farthest distance from node 0. Let's see, what's the farthest distance? The farthest distance can be, initially it can be 1, but if you just see that there are like 4 farthest distance, right? Which is 6, 4, 5, and 7. there are 4 farthest distance from the node 0. So we need to return any of this farthest distance. So start in the first run, start from any node and find the farthest distance from this starting node. So in the second run, we after we determine the farthest distance, which is in this case from 0, we can return, at the end we can return 7, let's say. So after we return the 7, then from this now start from the determined farthest node and find what is the farthest node from this starting node. And also at the same time we need to compute the distance between two farthest nodes, and at the end we need to return the maximum distance between these two nodes. Okay, let's look at this example. Start from any node. Let's say we're gonna start from node 0. Let's say start from node 0. Now starting node is 0, then farthest node initially it will be 1. Then because we are doing the BFS with Q, then we go through the 3, then we go 6. Then we need to visit every node. That's why we can stop here, but we also need to, there may be another node here, right? So that's why we need to visit every node in the tree. So let's say 6, then we're gonna come to 2, then 4, 5, and 7. So we return 7. So we determined that this is the farthest node from our starting node 0. In the second run of BFS, we start from node 7. Okay, node 7. From this node 7, now we start iterating again. We initially, now starting node is 7. Now we come to 2, then we come 4, 5, and 0, 1, and 3, and finally we return 6. So 6 is the farthest distance from the node 7, and the total distance between the node 7 and node 6 we return as 4. So diameter of this tree is basically 4. So this algorithm, we run this BFS twice on each tree. In the tree 1, we run this twice to determine the diameter of the first tree. And for the second tree, we do the same thing. We run this BFS twice. So after we find the diameters of each tree, tree 1, it returns diameter 1, and tree 2, it returns diameter 2. And we what we do, diameter 2. So we calculate the radius. We need the radius, right? We need the radius. We need to determine the center node, right? But we don't need to know exactly what the center node is, but we need to get the half of the diameter, right? Then we merge these two trees, and total diameter of the merged tree will be basically if there are 5 nodes, right? If let's say right now we have like 1, 2, 3, and 4, and the half of 4 is basically 2. Imagine if you have here like 8, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5, right? 5. We still have this 2, right? 0 is center node, and the distance will be, let's say, 5. We need to get the half. It will be half is 2.5. We need to get the ceiling of this. It will be 3, right? Basically, diameter of this will be half, basically plus 1. If it's not integer, right? Or we're gonna get the ceiling of this division. So then it will return us diameter of the first tree, the radius of the first tree, radius of the second tree, and 1 extra edge, because we need to connect that 2 nodes, right? So the merged diameter in the second example is basically 5. So let's recap. So there are a couple of steps that we need to do. First, we need to build the graph from edges, or we call it adjacency list for each tree. Then we compute the diameters of both trees using BFS and Q. And after we compute the diameters, we return the diameters, which is the maximum distance between the farthest, longest distance between any two nodes of a tree, right? Then we compute the diameter of the merged tree by getting the half diameter of the first tree and half diameter of the second tree, and we just add them, and we add the one edge. And we need to return the maximum of diameter 1 and the diameter 2, or the merged diameter. So this is basically all the steps that we need to do. I did not go through all the how we really computed this diameter or the longest distance between any two nodes of a tree, and that's basically BFS with Q. And I assume that you know this technique, right? This traversal. Now let's look at the code. Okay, so this is code. Let's walk through. So we are given the age 1 and age 2 of two trees. In the first step, what we do, we build the adjacency list, basically to, like, we are building the graph, and we are creating this by this dictionary. We look at the default dic and the list, and for each node we built a graph. So what each node of each graph is basically of the tree is connected to another node, right? And we built this adjacency list for the first graph and adjacency list for the second graph, and we see how many what is a node, how many, what's in, like number of nodes in each graph. And after that, we look at we compute the diameter of each graph. This is a bigger picture. So diameter of the first graph, and we return the diameter of the second graph. Then we merge. After we merge, we get the half of the first diameter and half of the second diameter, and we get the ceiling of it to account for additional edge, and we add one extra edge because that edge is we merge, right? Then we return this diameter 1 and diameter 2, maximum of this merged diameter, right? So and then this is we built this is a function to build the adjacency list, so to build the graph. Then this is a BFS section where we go through we pass total number of nodes, and we pass the adjacency list and the starting node, right? And this is needed to compute the diameter of a tree. So let's first look at the diameter of the tree. If the adjacency list is doesn't exist, so basically the graph or the tree is empty, it doesn't have any root or any node, right? Then initially we as you said, we first run the BFS to find the farthest distance from let's say from node 0, right? Any node, right? We start from 0, then we return the farthest node from that node 0. Then after that we run again. Instead of saying the 0, we pass this farthest node here, and after we pass this, then this function basically returns the diameter of the graph of the tree. So let's go through this BFS to find the farthest node. And initially, starting node, in the first BFS, we said we're going to start from starting node, and we add this to the double-ended queue. Then we initialize the set to track the visited nodes, and we initialize the maximum distance as 0. Then the farthest distance from the starting node will be that starting node itself. Then we loop through the queue. We get the size of the queue. Then for everything in the queue, we run the for loop. We pop the queue from left to get the node. And the farthest node, now we update to be the current node, right? Let's say from 0, and we need to go to the node 1, right? This farthest node will be node 1. Then we check the neighbor, each neighbor of that current node in the graph to see if that neighbor is already visited. If it's not visited, then we label or we tag them as visited. Then we add them to the queue to process later. So if the queue is not empty, which means that we added to go to the next level, then we increase the maximum distance to 1, and then we return the farthest node and the distance from that starting node, from the starting node to the farthest node. What is the maximum distance, right? What is the distance? So basically this BFS we run twice. One is like we start from node 0. In our case, node 0 basically exists, but we need to be careful because we may not have a node 0 here, but we need to randomly select any node. It works with any node. We can select any node and get the farthest node from that node and get the farthest node and run the same thing to see if we can compute the diameter of the node and the diameter of this graph and the farthest distance or farthest node from that node, right? So and the time complexity of this approach is n1 is the number of nodes in the first tree and number of edges in the first tree, and the number of nodes in the second tree, number of edges in the second tree. We run multiple for loops, but they are not nested for loops, so that they are still linear. The same thing for the time complexity. So yeah, this is basically the solution for this. It's very interesting problem in itself. So there are a lot of applications of this in social networks, right? And another real world network analysis, we can say in transportation planning. This roads and the connections, they represent as tree, right? And we can analyze their diameter, and it can assist us in optimizing this travel times and improving this connectivity between cities or the bus stops within the city, right? So yeah, this is basically the overall explanation of this problem. And yeah, if you have any questions, please comment, and let's just try to solve more of this kind of questions, and see you guys in the next video. Thanks, bye.